am Ishant Achyuta Sappa, and today I am presenting a project titled Adaptive Creative Fusion of Acoustic, Clinical, and Semantic Speech Features for Depression Screening. Under the guidance of Ms. V. Radhaman, this work falls under the domain of machine learning and proposes an explainable AI framework for automated, non-invasive depression screening using speech signals. Depression is one of the most prevalent mental health disorders worldwide and often remains underdiagnosed because current screening methods depend heavily on subjective self-reporting. To address this, we developed an adaptive multimodal depression detection framework (AMDD), which combines three types of speech features: acoustic features from log spectrograms, clinical vocal biomarkers, and semantic embeddings from Wavelet. These are fused through an adaptive gated fusion mechanism, and SHAP-based explainability is used to make the predictions clinically interpretable. On the DAIZ was dataset, the system achieved 88.46% accuracy, 0.909 AUROC, 0.842 F1 score, and 100% specificity. Let me now state the problem clearly. Current depression screening tools like PHQ-8 rely on subjective self-reporting, which is prone to recall bias, stigma, and underreporting. Most existing automated systems use only a single speech modality, making it hard to capture the full range of depressive indicators. Furthermore, many deep learning models lack interpretability, which reduces trust among clinicians and limits real-world adoption. These gaps motivated the need for an accurate, multimodal, and explainable AI-based screening system. Depression affects more than 280 million people globally and is a leading cause of disability and reduced quality of life. It is characterized by persistent sadness, loss of motivation, cognitive impairment, and emotional distress. Early detection is critical. It improves treatment outcomes and prevents severe mental health complications. However, conventional tools like PHQ-8, the Hamilton Rating Scale, and the clinical interviewers are largely dependent on clinician judgment and subjective patient input. Research has shown that depression majorly affects speech, including pitch, speech rate, pause behavior, articulation, and vocal energy. This makes speech a promising digital biomarker. Advances in AI and deep learning now allow us to automatically extract meaningful patterns from speech recordings. Unlike existing single modality approaches, my R framework combines acoustic features, clinical biomarkers, and semantic representations through adaptive gated fusion to improve both prediction reliability and clinical interpretability. We reviewed recent work in speech-based depression detection. A 2025 IEEE TAC paper used a hybrid CNN and BIGRU architecture with MEL spectrograms and MFCCs, but was evaluated only on non-English dataset. Continuing the review, a 2024 Journal of Affective Disorders paper emotion specific speech cues but had no end-to-end deep learning framework. A Neurocomputing 2024 paper applied attention-based fusion of MFCC and prosodic features but showed weak long-term temporal dependency model. A 2025 Journal of Voice Systematic Review identified jitter, shimmer, and HNR as key biomarkers but produced no deployable prediction model. Further, a 2024 speech communication paper used a transformer-based model for sequential speech modeling, but with high computational complexity. A 2025 ASM/TCH study compares short mobile speech recordings with clinical interviews but was not designed for hybrid fusion architectures. Finally, the DAIC was ACM AVEC 2027 provides clinical interview recordings with PHQ-8 labels. This is the primary dataset used in our work. There are three main issues and corresponding challenges in this domain. The first issue is that existing methods rely on subjective questionnaires. The related challenge is speaker variability. Speech patterns differ significantly across individuals in accent, vocabulary, and vocal style. The second issue is single modality limitation. The challenge here is fusing spectrograms, clinical biomarkers, and wave-LM embeddings. Transformer and CNN embeddings are difficult to directly map to clinical meaningful biomarkers. This slide presents the complete architecture of the proposed AMDD framework. The input is clinical interview speech from DAIC was dataset. The audio is first pre-processed. Participant speech is extracted by filtering the interviewer voice, converted into 16 kilohertz mono-channel audio, and then cleaned through noise reduction, silence removal, and amplitude normalization. The processed audio then feeds into three parallel feature extraction branches. The first generates log-mel spectrograms for acoustic analysis. The second extracts clinical vocal biomarkers, jitter, shimmer, pause ratio, and vowel space area. The third generates 3840 dimensional wave LM embeddings for semantic understanding. These three representations are fused using the adaptive data fusion mechanism, which dynamically learns the contribution of each modality. Finally, the fused features are used for depression classification and PHQ-8 severity estimation, with SHAP providing explainability. The project was implemented using Python 3.12 and PyTorch 2.x on Google Colab Pro, leveraging on NVIDIA Tesla T4 GPU. Key libraries include Librosa for audio pre-processing, Parselmouth for clinical biomarker extraction, WaveLM through the Hugging Face, SHAP for explainability, and the Streamlit 1.35 for interactive clinical dashboard. The DAIC was dataset with 16 kilohertz speech recording served as a primary dataset. Module 1 covers data collection and audio pre-processing. The dataset contains clinical interview recordings along with PHQ-8 depression severity labels. Participant speech was isolated by removing the interviewer Ellie's responses through transcript-based speaker filtering. All recordings were then standardized to monochannel audio at 16 kilohertz. Spectral noise reduction was applied, followed by silence trimming and amplitude normalization. The output is a set of clean, consistent speech recordings ready for feature extraction. Module 2 handles multimodal feature extraction processed speech recordings segmented into 20-second windows with 50% overlap to maximize speech coverage. From each segment, clinical vocal biomarkers are extracted. These include pitch mean and variance. Simultaneously, normalized 128 by 128 log ml spectrograms are generated for acoustic CNN input. WaveLM produces 3840 dimensional semantic embeddings that capture contextual and linguistic speech information. These three features sets from multimodal input to the fusion model. Module 3 describes the model training process and the adaptive gated fusion mechanism. Three parallel branches processed acoustic, clinical, and semantic features independently. These are then combined using a softmax-based gating fusion mechanism that dynamically assigns weights to each modality based on its relevance. This is the adaptive gated fusion. The fusion representation is then used in a multitask learning setup that simultaneously performs depression classification and PHQ with severity estimation. Model training used the Adam W optimizer when with dropout regularization, gradient clipping, and early stopping. Module 4 addresses model interpretability and modality analysis. SHAP was applied to quantify the contribution on individual speech biomarkers to each prediction. The analysis identified shimmer, jitter, overspace area, pause ratio, and pitch variability as the most influential indicators. Modality contribution analysis evaluated how much each of the three branches acoustic, clinical, and semantic contributed to the overall prediction. SHAP summary plots feature importance rankings. This visualization shows the SHAP feature importance rankings and the modality contribution analysis from our model, clearly identifying which biomarkers and which feature branches drive the depression predictions. Module 5 covers model evaluation and clinical deployment. The model was evaluated using accuracy, precision, recall, F1 score, AUROC, and the specificity confusion matrix. An interactive Streamlit dashboard was developed to allow clinicians to upload speech files and instantly view the waveform spectrogram, extracted biomarkers, depression probability score, modality contributions, and sharp explainability outputs, supporting real-world clinical decision making. Here you can see the pre-processing pipeline in action, showing the cleaned waveform after noise reduction and silence removal. This screenshot shows the feature extraction output, log mil spectrogram, and extracted clinical biomarker values. This is the Streamlit clinical dashboard designed to be simple and intuitive for healthcare professionals to use without technical expertise. Here we can see the depression probability output along with PHQ age severity estimation displayed on the dashboard. This screen shows the sharp explainability output, highlighting which biomarkers were most influential for the particular prediction. Here are the modality contribution charts showing how acoustic, clinical, and semantic branches contributed to the final prediction. And this final screenshot shows the model evaluation metrics displayed within the dashboard, giving a complete performance overview. This slide is the first set of reference in IEEE format, spanning publications from IEEE transactions on effective computing, BMC psychiatry, Journal of Biomedical and Health Informatics, and the original DEAIC was dataset papers from ACM AVEC 2017. These are the remaining references from the Journal of Voice, Speech Communication, Neurocomputing, and ACM transactions on computing for healthcare, covering the years 2024 and 2025. All 11 references collectively support the motivation, methodology, and evaluation approach of this project. Thank you.